You know, motion is absolutely everywhere. A car driving down the street, a leaf falling from a tree, heck, even the planet spinning through space. It's literally the most basic thing in the universe. But how do we actually talk about it? How do we describe it in a way that makes sense? Well, to get started, I've got a question for you, and it might be a little trickier than you think.
So let me ask you this. Are you moving right now? You're probably thinking, no, I'm sitting down watching this. But are you really still? The answer to that question, it turns out, depends entirely on your point of view. And figuring that out is the first huge step we need to take to really understand motion.
So, here's our game plan for this explainer. We're going to build this whole thing from the ground up. We'll start with that big question, are you moving? Then, we'll get into the big difference between the total path you take versus the shortcut. We'll find out why speed isn't the same thing as velocity, what acceleration really means, and finally, how a simple graph can tell the whole story of a trip.
Okay, let's really unpack that question I just asked you. The reason it's so tricky is that motion isn't an absolute thing. Like the title here says, it's all about your point of view. It's all relative.
I want you to picture this. You're on a bus. To the person sitting right next to you, you're not moving at all, right? You're staying in the same spot relative to them. But to someone standing on the sidewalk watching you go by, you and the entire bus are zooming past. And from your seat, the trees outside look like they're moving backwards. So who's right? Well, here's the crazy part. You both are. It all just depends on what you're measuring against.
So to solve this puzzle, scientists use something called a reference point. It's basically just a fixed background that we all agree on so we can measure motion from the same perspective. For that person on the street, the ground is their reference point. For you on the bus, the floor of the bus could be your reference point. The main takeaway here is huge. To describe any kind of motion, you have to pick a reference point first. Without one, saying something is moving is pretty much meaningless.
All right, now that we know we need a reference point, let's figure out how to measure a journey. And you might think, oh, that's easy. You just measure how far it went. But in physics, there are actually two totally different ways to talk about this, and the difference between them is super, super important.
Okay, so on one side, we've got distance. Think of this as your car's odometer. It's the total ground you covered, every single meter, every single turn. On the other side, we've got displacement. This is the shortcut, the as the crow flies, straight line path from where you started to where you ended up. And, this is key, it has to include a direction. A simple number like distance is what we call a scalar. But a number that has both a size and a direction, like displacement, that's called a vector. It couldn't care less about the winding road you took, it only cares about the start and the finish line.
And this little diagram right here makes this idea crystal clear. Let's follow the trip together. An object starts at point O, the origin. First, it travels all the way out to point A, that's 60 kilometers. Then, it turns around and comes back along the same line but stops at point C. So let's figure out the distance and the displacement for this whole trip.
So for the total distance, we just add up all the parts of the journey. Easy enough. It went from O to A, which is 60 kilometers. Then it went from A back to C. Well, if A is at 60 and C is at 35, the trip back was 25 kilometers. So 60 plus 25, that gives us a total distance of 95 kilometers. That's the total mileage it racked up.
But what about the displacement? Now remember the rule. Displacement only cares about the start and the end. It started at O and it ended at C. What's the shortest distance between O and C? It's right there on the line, 35 kilometers. Whoa, look at that difference. 95 kilometers of actual travel, but a displacement of only 35 kilometers. That shows you perfectly how different these two measurements can be.
Let's keep building on this. Knowing how far you've gone is cool, but knowing how fast you got there is usually what we really want to know. And just like with distance and displacement, physics has two different ways to talk about this: speed and velocity.
On the left, you've got speed. That's what the speedometer in your car tells you. It's just a number. It tells you how fast. Pretty simple. But on the right, we have velocity. Velocity is more specific. It's your speed and the direction you're going. So saying 100 kilometers per hour is a speed. But saying 100 kilometers per hour due east, now that's a velocity. And you can probably guess the connection. Speed uses distance, our scalar, while velocity uses displacement, our vector. See? It all connects.
So
we're putting together a really great description of motion. We know our position, how far we've traveled, and how fast we're going in a certain direction. But what happens when that velocity changes? What do we call it when we speed up, slow down, or even just take a turn? Well, that brings us to our next big idea, acceleration.
Now, here is a really crucial point, one that trips a lot of people up. Acceleration is not just speeding up, because velocity has both speed and direction. A change in either one of those things counts as acceleration. So stepping on the gas pedal, that's acceleration. Hitting the brakes, yep, that's also acceleration. Sometimes we call it deceleration, but it's the same idea. And get this, even turning a corner at a perfectly constant speed is acceleration because you are changing your direction.
And this quote gives us a really simple rule of thumb, at least for moving in a straight line. If you're moving forward and you speed up, your acceleration is in the same direction as your velocity, so we call it positive. But if you're moving forward and you hit the brakes, your acceleration is fighting against your velocity, so we call that negative acceleration. Getting those signs right is going to be super important later on.
All right, now for my favorite part. We can take all of these ideas, position, distance, velocity, acceleration, and we can actually draw a picture of them. We can tell the entire story of a journey using a simple graph. And let me tell you, it is an incredibly powerful tool.
So, let's start with some raw numbers. This table here shows us the distance a car has traveled at different moments in time. At 0 seconds, it's at the starting line. 2 seconds later, it's gone 4 meters. By 4 seconds, it's at 9 meters, and so on. Just by looking at the numbers, can you see what's happening? In each 2-second chunk of time, it's covering more and more ground. This car is definitely speeding up.
And here's what that data looks like when we turn it into a picture. This is a distance-time graph. You see how the line isn't straight? It's a curve, and it's getting steeper and steeper as it goes. That steepness, that slope, is a visual of the car's speed. And since the slope is increasing, it means the speed is increasing. That's what acceleration looks like on a graph. If it were a straight diagonal line, that would mean constant speed. And a totally flat horizontal line, that means it's not moving at all. Now let's compare two different kinds of graphs. On the left is the one we just saw, that distance-time graph with the curve showing acceleration. But look at the one on the right. This is a velocity time graph. Notice how this line is perfectly flat and horizontal. This tells a totally different story. It means that as time goes on, the velocity is not changing one bit. This object is moving at a steady, constant velocity. It has zero acceleration.
And here's a really cool trick hidden inside velocity time graphs. It's like a secret feature. If you calculate the area of the rectangle or shape underneath the graph line, that number you get is actually the total displacement of the object. It's an awesome visual shortcut for figuring out how far something went.
So how do all these things, displacement, velocity, acceleration, and time, all fit together mathematically? Well, they're all linked by these three incredibly powerful equations. They might look a little intense, but these are the master keys for describing any object that's moving with a constant acceleration. Real quick, S is displacement, U is your starting velocity, V is your final velocity, A is acceleration, and T is time. With these tools, if you know any three of those things, you can always find the others and predict exactly what's going to happen next.
And there you have it. You now have the complete set of tools to describe motion in a straight line, all the way from picking a reference point to using equations to predict the future. You get the key differences between distance and displacement, speed and velocity. But that just opens up another fascinating question. All of this works perfectly for a journey from point A to point B. But what about something that doesn't go anywhere, but just spins in place, like a wheel on a car or the Earth itself? How would you describe that motion? Well, that's a story for another day.